So we can look at these equations then and think of what these solutions look like from the graphing perspective. So when we do this, we need to be able to state the positive and negative possibilities, which gives us the domains of the piecewise functions. So when we look at this, we can look at the positive possibilities here. So for the positive possibilities, I have to think of what the domain is going to be. So the domain is when the inside is positive. So that's going to be when x is bigger than 3.5 or x is greater than or equal to 7/2. So that's going to represent the domain boundary of the inside, which essentially is going to give us the kink in the graph. Now there is also an outside domain restriction, and we're not really going to be too concerned by that, but I'm just going to show you that it does exist. Okay, so this is kind of an extra that is nice to know, but not a need to know. So when I rewrite it like this, I can also state as an outside restriction that x must be bigger than 0 because absolute value cannot equal negatives. Okay, so x must be greater than or equal to 0. But because when we put this together, we really just end up with the inside domain anyways. Okay, so it's actually not that relevant. So I'm just going to highlight the outside domain. It's not something that we're going to concern ourselves with too much. Okay, but it does exist. So once I get the outside domain, I'm going to rewrite this as a function. And if the inside is positive, the absolute value does nothing to it. And I end up with this equation, and I can simplify it to negative 3x minus 7. So this is a linear function. Okay, I'm just going to draw my axes here. It's got a y-intercept at negative 7 and a slope of negative 3. And the domain is from 3.5. So it's going to be something like this. Maybe there's my domain at 3.5. It's going to have kind of a steep slope here. I need to make sure that it goes through like this. And as I kind of trace it out like this, okay, so there's my 7/2. That is a straight line. The y-intercept is going to be at negative 7, but notice that that dotted part is the domain that doesn't exist. The solid part is the domain that we're going to work with. Okay, so that's the domain of from 3.5 to the right is the function. Okay, so that's the positive version of that. So then we need to move on to the negative version. Okay, the negative version has a domain restriction. Okay, so it's going to be the domain of that is going to be when x is less than or equal to, or we should just do less than. When x is less than 7/2. Okay, and again, x has to be greater than 0, and in this case, because we can't have the x equaling a negative, otherwise it doesn't quite work. Okay? But we're not going to, again, worry about the outside restriction. There's our inside restriction, that's where our kink is. And then I can rewrite this as with the negative version. So this is going to be when the 2x minus 7 is going to be the negative. So we need to make this inside negative into a positive. So we're going to do that by making it the opposite sign. I can now then graph this. This becomes negative 7x plus 7, okay, as the outside function. So from 3.5 to the left, it's going to have a slope of negative 7 and have a y-intercept of positive 7. So it's going to look like this. Okay, so I'm going to draw this a little bit nicer. Okay, so the y-intercept is at positive 7, and the graph does continue that way, okay, and it looks like that. Okay, so I have my solution is going to be at that point there. Okay, it's going to be, there's my real solution. I do have an extraneous solution that's going to show up on the green. Okay, oops, it's going to be on the green. Okay, so if I solve this, the the green part of this, I will end up with this extraneous solution over here. So I'm going to go ahead and solve these. Okay, so when I solve this part here, it's going to be negative 7x plus 7 equals 0. X is equal to 7x is equal to negative 7. X is equal to 1. And I can test this, but I can also see that x equals positive 1 is my real solution. If I go ahead and solve the negative version, okay, so here I'm going to end up with negative 3x minus 7 equals 0, negative 3x equals 7, x equals negative 7 over 3. Well, there's my negative 7 over 3. Okay, and it is an extraneous solution, so this is extraneous. Okay. So, a couple ideas here then that I want you to focus on is that we have this positive and negative domain that allows us to write this as a piecewise function. Okay, when we look at the domain restrictions does allow us to determine whether our solution is extraneous or not. Again, the easier way would be just to substitute it in and see if it actually works. The domain boundary is where the kink is. Okay. And again, here I can draw this as a piecewise function. This is for the negative domain in red. This is for the positive domain in green. And because it changes, absolute value does something to the graphs, it actually kinks the graph at that point. So that's where the vertices and kinks show up, is at that domain restriction. So when I graph this, I have the green part here. The green part is going to be negative 3x minus 7, and it has in the domain of bigger than 7 over 3. And then less than 7 over 3, we have negative 7x plus 7, which is the red part of that graph. Okay. So does this equation have an extraneous solution? And if we solve this algebraically, yes it does. Because if we algebraically solve, which we did here in green, it does have extraneous solution. So yes, it does have extraneous solution. Okay, I'm just going to put it in green. Okay. It is where the graph crosses the x-axis outside of the domain. So outside of the domain. Okay, so this is how we can analyze. Now, if we just graph it, we can just look at the graph, plug it into our Desmos, and we can see exactly where it is. We should be able to anticipate now extraneous solutions based on extrapolating, okay, the graph beyond its domain, and we can see that where some extraneous solutions may exist.